Welcome to today's FuelSum webinar. My name is René Eaton. I am senior researcher at the Zurich University of Applied Sciences in the Life Cycle Assessment Research Group, and it is my pleasure to guide you through today's webinar on the topic of multiple fuels, one SOFC, how does it work? This webinar is part of the FuelSum project. The FuelSum project focuses on a novel propulsion system for maritime shipping that relies on one hand on the SOFC technologies, so using fuel cells, and on the other hand of the use of different synthetic fuels, including ammonia, methanol, as well as hydrogen. Today's presentation will be held by Peter Strinko. Peter is responsible for the work package 3 of the FuelSum project. He is a development engineer at AVL Hungary, and he was responsible for the testing phase and the operation of the test bench for this SOFC system at the AVL Hungary facilities in Kecskemét. After the presentation, we will have a Q&A. So yeah, please prepare or submit any questions during the webinar if there are any. But now, without further ado, we move on to the presentation by Peter.
Thank you, René, for the introduction. I'm Peter Strinko from AVL Hungary. And as René mentioned, today's topic is multi-fuels, one SOFC system. How does it work? So I would like to give you an insight of how we can design and how we were design the multi-fuel SOFC system for the FuelSum project. So yeah, here's a quick info chart from me. I work at Kecskemét at AVL as a development engineer in fuel cell topics, but I would like to jump over it quickly. So about today's agenda, small introduction about the topics. After that, I will go to the technical details. Like fuels, system parameters, efficiency, architectures. After that, a quick overview about the whole topic. And as René mentioned, at the end, we will have a Q&A session. So a really quick recap of what we did in the FuelSum at AVL side. You can see we were included in a lot of different tasks. But for today's, we will describe the task and the carried out work in the task 3.1, which is basically the system modeling, simulation, and analysis of the integrated system with multiple fuels. So I would like to jump into the overview. So the main questions. First of all, why SOFC? Why we are speaking about SOFC in maritime application? First of all, with SOFC, high system efficiency available, and this could give us a benefit if we would like to operate a vessel around the world. And the second and really important point as well, the decarbonization potential, because nowadays has a lot of focus on this. So you will see that two of the proposed fuel not containing carbon at all. The third is it's containing carbon, but it's also can be used in a circular way. So in the next webinar phases, there will be a more and more discussion about that one. So the second question, why multi-fuel? Why we would like to design and apply a multi-fuel system for an ocean-going vessel? So first of all, then we have a flexibility for the ship operators, because if you are operate a vessel around the world, it's will be a mandatory requirements to visit different ports around the world, and the different ports maybe will not have all the same architectures in the future for the alternative fuels. So if you have multi-fuel options, you have a flexibility to make different routes with different ports which offer different fuels in the future. And another point why we would like to work with multi-fuel system is the economic potential. So if you have an option to choose from which fuel would like to use, then you will most probably choose the cheaper one. And the third main question is by ammonia, methanol, or hydrogen. It's an answer. It's quite easy because in the fuel consortia we foresee these three alternative fuels as good candidates for the futures, which could spread around the world in the maritime industry. So these were the main questions, but now I would like to quickly give an insight about the main challenges. So actually, the first biggest challenge is to really design a system which is capable of operating in high efficient operation for these three different fuels. So yeah, it's not an easy job. I think in an engineering world, if you would like to use a multiple criteria system, it's getting more and more complicated, and this is not the fuel cell systems are not an exception as well. So another main challenges which were in a big focus in the fusion project to develop a fuel processing unit which is capable of reforming the methanol and cracking the ammonia as well. So because making these two processes in one component, it's not an easy task for today's industry. And the third challenge is how we can apply this SOFC system for big vessels in the megawatt ranges. So these are the main challenges in the FuelSum project. And now I would like to jump into the technical details. So first of all, if we are speaking about different fuels, I would like to quickly go through the different properties of the different selected fuels. First of all, the methanol. It's really important that pre-process is essential for methanol because, SOFC, it's capable of using different fuels in a flexible way, but for in methanol case, you need to pre-process the fuel at least in some portion of that. So for that, steam methane reforming is required. And because of this, the steam reforming, you need steam. So that's why single pass solution is not really feasible if we would like to make an efficient system, because then you need to evaporate the water. But if you make the recirculation, then you can use the produced water from the fuel cell stack, and in this case you can higher up the system efficiency. As I mentioned, internal reforming is possible, but it's limited, so we need to find a balance between this, the internal reforming and the pre-processing. And also, if you are speaking about the fuel properties, environment and health effects are really important. So it's need to mention that in case of methanol, carbon monoxide will be present in the system, which is highly toxic. So this point need to be cared quite with a high importance. The next point is the ammonia. First of all, I would like to highlight the ammonia. It's quite an aggressive agent. It's quite corrosive, especially in high temperatures. So special material need to be selected for all the components, as well as the stack and the other BOP components, which are operate at high temperature. So again, internal cracking is possible, which could give us some benefits, which I will tell you about more in detail in the next part of the presentation. And also we can state that usually nowadays the stack providers state a limit which about ammonia content at stack inlet. So you can use internal cracking, but not with unlimited potential. So, and again, safety concern, ammonia is highly toxic, so you need to be investigate the safety aspects quite in detail. But ammonia is handled worldwide over 100 years, so we have the processes, but need to be considered quite strictly. So the hydrogen, hydrogen not need pre-processing at all, so just temperature control need to be done before we let hydrogen into the stack, which is making life easier. But on the other hand, there is no internal cooling effect inside the stack. So another points which we need to take care. And again, I would like to highlight the safety concept, because from explosive protection, hydrogen is the most critical fuel from these three. So this was about the fuels. So now I would like to jump over for some system parameters. First of all, I would like to discuss a bit about the fuel of gas recirculation, because if you would like to increase the system efficiency, you need to be recycle the fuel, because the fuel cell stack usually it's not capable of operating really high fuel utilization. So it's mean that you will have unprocessed fuel at the stack outlet, and if you are not recycle it, you will lose that potential. So that's why recirculation, it's at least need to be considered if you design an SOFC system, but of course it's a complexity into the system. And if we are discussing about recirculation, another topic it's need to be considered. This is the water discharge, because at the product as a product gas at the fuel outlet side, you will have a lot of steam generated from SOFC operation. But if you are recircle that one, you will get some kind of effects which the water content will cause into the system. For example, methanol is really useful, but for other fuels it's not really. So this will be also discussed later on. So another system parameter is the fuel processing unit temperatures, because the fuel processing units it's working in a way that if you are changing the temperature, the processing will change, and the outlet gas composition will be different. So because of this, the fuel processing unit temperature is a key system parameters. In a methanol case, if you are shifting these temperatures, the methane content after the fuel processing unit and before the stack at the stack inlet will change. At the ammonia content, ammonia case, also the ammonia content will change if you are change temperature. And if you change these two gas composition or to gas concentration at the gas composition, the SOFC stack operation will change drastically. So you can see here the temperature is the main parameters, and the ammonia and methane concentration will change according to that parameter. After this, you can see that the thermal control of the stack is really important, because the internal cooling can be utilized in case of methanol and ammonia case, because the methane steam reforming and ammonia cracking inside the stack has a cooling effect inside the stack, which is beneficial, because if you do not have this effect, you can have just another parameter which can vary, is the air volume flow. And if you are increasing the air volume flow, you increasing the parasitic losses on the air blower, which decrease your system efficiency. So that's why this kind of temperature control of the stack is quite an important parameter in SOFC systems. So an overview slide here to give an overview of the different trade-offs which we discussed. So you can see here three different trade-offs, like water in the recirculation, fuel processing, and stack thermal control. And you can see that different fuels has different trade-offs. So I would like to highlight that this is really a colorful slide, and the colorful it's really meaning that it's not easy to decide on these different trade-offs in a multi-fuel system, because different trade-offs for different fuels give different requirements for the system build-up. For example, water in the recirculation, it's really present in methanol case, but it's not present or give better efficiencies if it's not present in ammonia and hydrogen cases. And also for fuel processing unit and stack thermal control, you can see different fuels has different requirements. So after we discuss these trade-offs, I would like to show you how we define the system efficiency for these different fuels, because in order to make a comparison, system efficiency, of course, it's a really good indicator for that. So we are set up a methodology which we called internally a V0 parameter study. What does it mean? It's mean that we are consider some main components inside the system, like the stack and the fuel processing unit, but not considering the whole heat exchanger network. But we made some kind of simplification on that and made some kind of system parameters which could indicate the efficiency of the heat exchanger or other system parameters. So this parameter study had a lot of parameters which is able to vary. Some of them are related to components like stack and reformer, inlet-outlet temperatures, inlet-outlet pressures, and others. Mostly other parameters are mostly connected to system like recirculation rate, current load, fuel and airflow, and also the heat exchanger or heat recovery efficiency, and also the different discharge in the recirculation part. So this is a really good tool to make the first investigation on different fuels with the different main components like stack and fuel processing unit. And after that, we will have a good input for the more detailed system design and investigation. So I would like to jump to efficiency topics and different system parameters. As usual, I will start with methanol. So in this chart, you can see the system efficiency with green, the recirculation rate with blue, and direct internal reforming with this orange color. So I would like to first describe the direct internal reforming. This is actually the methane content of the stack at the stack inlet, which will be reformed internally at the stack. So this is really good parameters which we can vary and which we can investigate. The effect of this parameter on the system performance. And you can see here in part load and full load, there is a high direct internal reforming rate, but at the middle of the load range, we have lower ones. So I would like to highlight that we investigated the 3 kilowatt system for this study, and you can see here we started from 1.5 kilowatt and at 3 kilowatt. The reason is that because beside these two values, the system start to operate quite inefficiently. So we define the operation window between 1.5 kilowatt to 3 kilowatts over the whole investigation. And you can see also that the efficiency has a peak about 80% of the load, and at the full load we had some kind of percentage lower. This was the main outcome from for methanol. I would like to jump to ammonia operation. Here I would like to highlight two interesting parameters which we were investigated: the water discharge in the recirculation rate and the uncracked ammonia at the fuel inlet. So first of all, you can see the water discharge effect on the system efficiency. So you can see here, if you are starting from lower water discharge, or without water discharge, we have the baseline, and if you are increasing more and more the system water discharge, the system efficiency will increase as well. So we can state that water discharge for ammonia, it's beneficial for sure. And if we are checking the ammonia content at the stack inlet, we have a quite different view on that. So again, we have a starting point with this yellow color, and you can see here, if we are increasing the ammonia content at the stack inlet, we have increased system efficiency. But if we are increasing more and more, we have lower and lower system efficiencies. The main reason behind this, that if you would like to have higher and higher ammonia concentration at the stack inlet, you could not be use recirculation, because if the fuel goes through the stack, inside the stack, the ammonia will crack. And if you are recirculating, then hydrogen and nitrogen content will increase. So that's why if you would like to reach higher and higher ammonia content at the stack inlet, the recirculation rate will need to be lowered and lowered, and this has a negative effect on system efficiency. So that's why we are found out that direct uncracked ammonia content at the stack inlet has an optimum around 16% of ammonia content with a 90 to 100% water discharge. So this is a good point for from system integrator point of view. So if we have a stack which is capable of handling about 20% of ammonia, direct ammonia content at the stack inlet, we are quite happy with that, and the stack providers should not need to target 100% pure ammonia capability with their stack from system integrator point of view. And the our third fuel is the hydrogen. Again, here two main parameters were investigated. First, the recirculation scenarios, and then after that, water discharge. So in this diagram, you can see here the lowest graphs show the single pass solution when we not applied recirculation in the system. You can see here that this is this has quite significant efficiency difference or disadvantages over the other solutions. And the other solution is the case when we have recirculation in the line, but we do not apply water discharge. And the third scenario, we are using recirculation and water discharge in the system. So again, water discharge has a nice effect on that. And we made a more detailed investigation regarding this parameter because we investigated how the water discharge rate affect the system efficiency. So you can see here, if you are increasing the water discharge from 0 to 30%, we have a quite big efficiency jump. But after that, we have lower and lower gains for system efficiency. So the main message about this water discharge effect, that if there is a possibility to discharge any water in case of a hydrogen system, it's really worth to do that one, because you can gain easily big portion of system efficiencies. And if the system is not able to remove all the water from the recirculation line, it's not a big problem. So here I would like to give you a comparison between different fuels. So you can see here that the hydrogen and methanol perform quite similarly for all the operation range, but for the methanol, for the ammonia, from about 75-80% of the load range, there is an advantage regarding system efficiency. But I would like to highlight that in this case, recirculation and water discharge from recirculation was considered for this kind of scenarios for hydrogen and ammonia case as well. So this was the part where I discussed about the efficiency topics. Now I would like to move forward with some kind of system architecture decisions and trade-offs which we need to consider. And as usual, fuel processing unit is a key component, and operation of that key component is really essential for the system. And as you can see here, as all the time, the different fuels has different requirements on that. So you can see here the temperature range for the methanol reforming. It's not really overlapping the temperature range which is required for ammonia cracking. And also the heat demand is different because ammonia require much more heat input than the methanol reforming. So and another aspect in a system design or system architecture design, that from where you can put heat into the fuel processing unit. So here I put two possibilities. The first is the stack of gas, mainly the stack air of gas, which containing quite big heat portion and can use for fuel processing unit. But you can see here the temperature range is limited. I mean the maximum temperatures which we can use. And if we would like to go higher, we would need to include an oxidation catalyst where we can use some kind of fuel to produce more heat and high temperature level heat. But of course, this usually requires fuel which is not beneficial for the system efficiency point of view. Again, main message here that for multi-fuel operation, you need to consider quite different requirements for different fuels. So that's why the optimum point, it's really hard to find. The next point regarding the system architecture discussion is the recirculation options, because as we see already, most of all the cases need recirculation, fuel recirculation, if you would like to reach high efficiency operation point. So basically two kind of recirculation solution is possible. First, the active recirculation, which is done by a recirculation blower, and passive recirculation, which can be done with an ejector. So you can see that the two different solutions has different advantages and disadvantages. Basically, the ejector is quite a simple component and really effective, efficient to use, because you can use the usually the pressure pressure in the input fuel, so it's not need any other power from outside of the system. So actually, no more losses to the system. But on the other side, the ejector it's really hard to control, and there is narrow operation windows where the ejector could work efficiently. On the other side, the blower, it's quite a complex components and required usually electrical power to drive. So this is an additional loss of the system. And but on the other side, easy to control, and it's possible to operate in wide operation range. So this is again quite a tricky decision if we would like to make a multi-fuel system architecture. Now, as we discuss some of the main decisions in the system architecture design, I would like to present our flow sheet, which was defined for the fuel sum project. So you can see on the chart. But basically, if we quickly go through the main parameters for that, first of all, we have a fuel processing unit which is capable of processing the methanol and ammonia as well. And we are heated that one with the stack air of gas. Of course, that heat could be controlled because we have a bypass line, so we can decide how much stack air of gas can go through the fuel processing unit and how much it's bypassed. On the other side, we have a recirculation, of course, fuel of gas recirculation, and we selected the active recirculation with the blower. And on the other side, no water discharge was applied for this system because we would like to reduce the complexity. Even the system is quite complex, and we do not want to further make the operation hard. And actually, usually on the vessels, not cooling power is not easily available. And the last 2 points which I wanted to mention, we applied the central fuel processing unit, which is preconditioning all the three fuels to maintain the pressure and temperature levels which could go into the SOFC unit. And on the other side, we implemented the startup heater because on board the ship, electrical heating, it's not a really big possibility, because you would like you do not want to install a lot of battery to be able to heat up your system. But if you are preserve some fuel for startup heater, it's really easy to apply, I mean, the heat up. And if we are jump over and we can discuss the system efficiency for this proposed multi-fuel system architecture, and you can see again a graph where you can see two different results. The first result is the V0 results, which I implemented to or introduced you before that, and you can see the results from that V0 parameter study with solid lines for the proposed architecture for all the three fuels, and you can see crosses. The crosses are really a detailed investigation with real flow sheet considered with real components in a simulation. And you can see here that two things actually. First thing is that the trends are the same for hydrogen, methanol, and ammonia. You can see the same trend curves in case of V0 and V1 simulation as well. But on the other hand, you can see some kind of offset, some kind of decreased system efficiency for the more detailed investigation. Why we do have one? Actually, the reason is really simple. We made conservative estimation on different parameters like heat exchanger efficiencies, because we have different heat exchanger in the detailed layout, and also the electrical inverter efficiency was considered quite conservatively in our detailed system investigation. And also we have limitation from the multi-flow approach, so no water discharge was applied, and same components was used for different fuels, which is of course not ideal, because in some case of different fuels you will not operate that specific component in the best optimum. So actually now we arrived at the overview. I would like to highlight three main points. The first, that multi-fuel system is feasible and results reasonable efficiency over the whole defined operation range for all the three fuels. So this is, I think, a message for the industry. And also the second one is that if you consider a multi-fuel system, you will have some kind of trade-offs, and one of the trade-offs is that if you are consider a specified system with a specific fuel, you will have a system efficiency advantages for that. So this is really depending on the use case. So we now arrived at the third point at this overview slide, the use case, because I would like to underline that the use case will define really the solutions for SOFC application in the maritime industry, not just in the maritime industry, but all the industry. So really the use case will define the system and the behavior of the system, but we are able to design for all fuel use cases fuel cell system. And last but not least, I would like to highlight some technical challenges which we were faced during the FuelSum project. And also, I think if anybody else will would like to develop a multi-fuel SOFC system, we will face the same challenges. First, the water management. This is the water management in the recirculation line. I think after this webinar, you can have a feeling that this is a quite a crucial point in multi-fuel SOFC system. Secondly is the fuel processing unit. It's again really components which need to be tailored for the use case, the use fuels, and it's really need to be investigated more in detail to find an operation point where all the applied fuels can be processed in a nice and usable way. And the third challenge is to meet the limitation of the main components, especially the stack, because different fuels will result different operation parameters. For example, operation temperature or mass flow in fuel side and air side will be different for different fuels, and it's really tricky to withstand all the stack limitation with this wide range of parameters, main parameters. So these are the main technical challenges which we are faced and which we are tackled during the fuel sum projects. So that was it from my side. So we can go into the Q&A session. We can make an open discussion about this topic.
Perfect. Thanks, Peter, for this technical and very insightful presentation. We already received some questions for the Q&A, but still last call. If you have questions, the sooner you submit the questions, the more likely it will be that we have time to answer them. So last call. So, but with this, we move on to the Q&A. And one of the first or most raised question was, is this stack or SOFC stack system capable of operating with all these mentioned fuels?
I mean, yes, of course, our used stack is capable of working with these fuels. This stack coming from our project partner Alcogen. But yeah, different stack suppliers would have different limitation on that. If we are go through the three examined fuels, first, the hydrogen. Most probably, stack suppliers will not have a strict requirement on hydrogen side, but in methanol and ammonia case, there should be some kind of limitation. For example, methanol case, the mentioned direct internal reforming rate could be a limitation from the stack providers, and also in case of ammonia, it's also the pure uncracked ammonia could be a limitation from the stack providers. But if you use a pre-cracker in the system, you can crack all the ammonia and you will end up in hydrogen and nitrogen operation points, which most probably be suitable. So yeah, my short answer is yeah, most probably the stack providers are capable of operating with all the mentioned fuels.
Okay. I think this is already very impressive to have this amount of flexibility with the fuels going into this fuel cell system. I think
Yeah.
connected to this question, there was another question on would the system also work with other fuels, or is it limited to these three types of fuel with ammonia, methanol, and hydrogen?
Really nice questions, because yeah, usually methanol and ammonia, for example, not the first choice in case of SOFC. Of course, natural gas and LNG and other carbon containing fuels could be used in case of SOFC systems. In FUSAM, we are selected the specified three fuels because they are quite interesting, and they are a good application, good chance that they will be used in the future in the alternative fuels. So yeah, definitely there are a lot more fuels which could use in an SFC system. And I would like to just go back to your previous question or previous comment for the previous questions, that yeah, this flexibility is quite fascinating, and really this is one of the reasons why we are would like to use SFC, because that has a quite big flexibility in case of fuel in an SFC system.
Okay. Then we had another similar question, or going into a similar direction. Are there any other fuel cell or fuel processing system currently available that are able to handle this amount or this many different fuels as this
Mhm.
system?
Yeah, as I highlighted in my overview, this is really a challenge because, as far as I know, and as far as we know in the FuelSum project, there is no off-the-shelf components which are able to handle this kind of quite different fuels in one component. So it's quite unique. Our colleagues at VTT made a nice job to provide our fuel processing unit for FuelSum, but this is definitely key components which need to be investigated further in case of multi-fuel SOFC system in the future.
Okay, yeah, thanks for this. Then we move on to other question, maybe more technical. Um, yeah, would is it possible to have a system working also without this recirculation system?
Yeah, yeah, it's again different fuels has different requirements. So for ammonia and hydrogen, yeah, it's quite possible that without recirculation it's could work, no problem at all. And if the stack could reach 95% fuel utilization, it could make a viable option. I mean the single pass solution. But for methanol, as I mentioned, the steam reforming methane steam or methanol steam reforming, it's really mandatory, and for that steam it's required. And supplying steam from outside of the system, it's really inefficient. So for methanol, this fuel recirculation is really needed to supply the steam for the steam methane reforming process. So my short answer is for methane, the recirculation is really needed. For ammonia and hydrogen, it's need to be investigated use case by use case.
Then also on the more technical level, this water discharge option, is this necessary or does to include this, or does it make sense to
Mhm.
include this?
Good question. Again, it's really connected to the previous one. Yeah, in methanol case, I would like to not describe further because we stated that for methanol we need water in the recirculation. But in case of hydrogen and ammonia, as you can see in the FuelSum project, we not apply this water discharge system. So it's really the system it's capable of working without this water discharge solution. But as I showed you during the presentation, as soon as you have water discharge in the system, you have efficiency increase immediately. So if pure hydrogen or pure ammonia system would be designed, then a water discharge solution would be really useful. So I would use that one. So again, use case by use case. In a multi-fuel system, we not apply that. But if we would like to go to a pure ammonia solution or pure hydrogen solution, most probably apply that solution.
Okay. Yeah, thanks for again these elaborate answers. And maybe we switch the focus a little bit. And one question was also looking at the requirements for maritime shipping and
Mhm.
comparing these systems to conventional internal combustion engines that are currently used for container ships in marine shipping. Yeah, what are differences when we move to SOFC system that is multi-fuel capable?
Mhm. Yeah. First of all, I would like to highlight why we are considering the SOFC in for example, replace the internal combustion engine. The first solution is the first answer for this question is the efficiency. Still, with the SOFC system, we can reach higher system efficiency, and that will reduce the fuel consumptions. And in a vessel lifetime, the fuel consumption is really a big portion of the cost of the ownership. But I think you and your colleagues will have a different lectures on that. The life cycle assessment for this. So I will give the chance, of course, to you to describe that in the next webinar. I guess we will have a webinar series on a webinar part in this series on that, right? Okay, cool. And another point, yeah, sorry.
No,
Okay.
please continue.
Just a small comment regarding this comparison. What's the difference between IC and SOFC? So in the big ships, even in the large ships, usually you have one or two IC, but not a lot of IC. You can increase the IC power quite dramatically into multi-megawatt ranges. But for SFC system, modularization it's a key point, because we also had a look how multi-megawatt SFC system would look like in a maritime application, and we found out that we call it single unit. The size of the single unit would end up around 1 megawatt. And why we are calling it single unit? Because we can control that unit separately, and you can switch on and switch off these units. And if you would like to, for example, build a 10 megawatt ship, you can put 1 megawatt single unit, and you can use that according to the requirements. Even you can shut down one single system. So this is a really big difference between IC and SOFC application in maritime sector.
Okay. Yeah, thanks again. I think we're approaching the end of the Q&A session. Thanks for all these very interesting questions. I would like to wrap up with one question from my side. And this question is, given if you look at the wide variety of fuels that could be utilized by such a system, if you had to focus on one particular one with all these trade-offs and different requirements, which one would you pick? Would it be methanol, ammonia, hydrogen, methane, liquefied natural gas, anything else, or which one would you choose just from an engineering perspective?
Yeah, really, it's such a good question. But again, I don't want to hide against the answer. But my answer is that really the use case will define. Because, for example, from my side, hydrogen would be a viable option. But if you would have an ammonia carrier vessel, then I think ammonia would be really used in that case, because anyway you need to take care of the safety concerns of ammonia. So that totally makes sense to apply an SFC system fed by ammonia. For example, LNG carriers, it's really a big topic right now, and if you have an LNG carriers, I think it totally makes sense to use the LNG inside the SFC system. So my answer is again, it's really depending on the use case. I think SFC, it's as we described, it's quite flexible, and SFC system can operate in a good, efficient way with a lot of different fuels. So yeah, I hope it's a good answer for you.
Mm-hmm. I'm happy with the answer.
Okay, cool.
So yeah, with this, we are at the end of the Q&A session. Thanks, Peter, very much for this presentation, as well as for these many answers on these different questions. And thanks for the audience and for the interesting questions. Furthermore, I would like to thank Albert and Kerstin and the team from AVL that supported the technical side of this webinar recording. And I think with this, we wrap up. And it would be my pleasure to welcome you in any of the other webinars of the webinar series on the Fuel Zone project.